Hello student, today we are going to study a new topic, that is magnetism. It is related to class 12th physics syllabus. Magnetic effect of current, to be precise. See what we had. First of all, we had Oersted experiment. See what he did was that he took the magnetic compass over here near a current carrying conductor. He saw that when a current is passed in a current carrying conductor and when we place a magnetic compass near it, it shows deflection. From here he came to the conclusion that a current carrying conductor produces magnetic field around itself. And when he saw that he reversed the direction of current, the deflection of the magnetic compass also get altered. So here the first observation was that the current carrying conductor produces magnetic field around itself. But we always know in physics that we have to precisely measure anything, and whatever the factor it depends on, we have to be bang on the target. Okay, what actually it will have. So then we had a scientist, Biot, savart. He said that suppose we have a conductor over here and the length of this conductor is, let us suppose, delta L, and the point P is over here. He said that the precise value of magnetic field due to the current carrying conductor will be equivalent to what? He said that the strength of the magnetic field will be directly proportional to the current pass, directly proportional to the delta L is the length of the conductor. It is directly proportional to the sine theta. This sine theta is basically the angle this element make with the point P. Then we said that it is inversely proportional to the square of distance between them, this current carrying element and this point P. And summarize all this thing into V0 upon 4 pi I dl sin theta upon r square. And this is what he said, that mu0 upon 4 pi is basically equivalent to, it is basically constant, it is equivalent to 10 to the power minus 7. Then utilizing his observation and formula, we were able to derive loads of variable type of current carrying conductor. Let us suppose what we have, a circular current carrying conductor. Then we said that how much the magnetic field it will contribute at the center of the coil. What we have? Magnetic field at center of current carrying conductor. See what we have. We know that Biot's law, that is V0 over 4 pi, this is I dl sin theta upon r square. We'll utilize Biot's law. See how come? Let us suppose this is the delta L. So this element makes 90 degree, and delta L, suppose integration of whole of this length. This is delta L. Whole circular element will be equivalent to what? If it has radius r, then delta L will be equivalent to what? It is circumference of a circle. Sin theta, we know that the tangent makes 90 degree, it is equivalent to 1. What we do is that we place the value over here. It is coming out to be what? V0 I, delta L is what? 2 pi r, sin theta 1 upon r square. This get cancelled out. What we are left with? V0 I upon 2r. And suppose in the question they do say that what is the net magnetic field, it will be equivalent to, suppose it has n number of turns. In that case, it will be mu0 I upon 2r into n. This is the magnetic field at the center of circular current carrying conductor. Then we move on to what is the magnetic field due to straight current carrying conductor. This is very important formula. Magnetic field due to straight current carrying conductor. Current carrying conductor. See what we have. Let us suppose this is our current element. We have, this is point P. This is delta L. Again we will be utilizing the Biot's law to find the total magnetic field to this element. Let us suppose this is, it makes angle theta over here. This is angle phi. Let us suppose this is at a distance x from the conductor. This is, let us suppose L. This is R. Again we know that Biot's law is what? Delta B mu naught upon 4 pi. This is what? I dl sin theta upon r square. This is what? Biot's law. We'll utilize this to find the magnetic field due to straight current carrying conductor. How come? See, we have like, this is, see, these are varying element. Delta L, sin theta, r changes when the position of this changes. So what we'll do is that we'll convert this varying element into one element, that is in term of phi. How come? See, we know that this is 90 degree. First part will go theta plus phi is what? 90 degree. Theta is what? 90 minus phi. We need to know sin theta. Then sin 90 minus phi is coming out to be what? Cos phi. We have dealt with one hassle, that is sin theta has become cos phi. Now we'll go for like tan. This is delta L. We can go for like tan phi is basically what? Perpendicular by base. This is L upon x. This is x tan phi L. We'll differentiate this out. It is coming out to what? Sec square phi delta L. This is, we have dealt with delta L also in terms of, we have converted this into in terms of phi. Then we'll go for cos phi. Cos phi is what? Base upon hypotenuse. This is x upon r. R is what? X upon cos phi. R has become x sec phi. See, what we will do is that we'll utilize all these values and we'll integrate that out to get magnetic field due to straight conductor. See what we have. This is, we have delta B is what? Mu naught upon 4 pi I dl sin theta upon r square. See what we have converted. Sin theta we have converted in term of cos phi. Delta is x sec square. We'll place this value over here. This is mu naught 4 pi I. Delta L is what? This is x sec square phi del phi. Sin theta is what? Cos phi. And R is what? X sec phi. So it becomes what? X square sec square phi. See what we have? X get cancelled out. This is what? Mu naught upon 4 pi I upon x. Integration is what? Cos phi del phi. It goes from minus phi 1 to phi 2. So what we need to do is that we need to integrate cos phi. It becomes what? Mu naught upon 4 pi. This is I upon x. Cos phi becomes what? Sin phi. It goes from minus phi 1 to phi 2. This is mu naught upon 4 pi. This is I upon x. So upper limit is what? Phi 2 minus sin minus phi 1. It is coming out to be what? It is mu naught upon 4 pi. This is I upon x. This is sin phi 2 plus sin phi 1. Suppose we take the case of infinite conductor. First, infinite conductor. In that case, what will happen? Means phi 1 will be equivalent to phi 2 is equal to 90 degree. In that case, it will become mu naught upon 4 pi I upon x. This is 9091. So it is this. This is magnetic field due to infinite conductor. This is very important formula because this final formula has been utilized everywhere. Now suppose we have like conductor like this. It goes from this point to infinity. In that case, it will be mu naught upon 4 pi I upon x. That's it. Not double. Because this point over here it is 0. It's clear? Now we will move on to magnetic field on the axis of circular current carrying conductor. Magnetic field due to circular current carrying conductor on the axis. On this axis we will calculate it out. What we have, this is magnetic field on the axis of circular current carrying conductor. See what we have. See, this is circular current carrying conductor. On the axis of it, we have to calculate magnetic field at this point. So what we have, this, let us suppose the radius of circle is a. This is x. See, we see that the direction of magnetic field is like this. This is phi. Suppose this is angle phi over here. So it has like phi over here, phi. This is the resultant magnetic field is acting along this direction. Now what we will do? Let us suppose the value of is delta B over here. Delta B over here. We'll go for the component part. It is delta B cos phi over here, and delta B cos phi, and delta B sin phi, and delta B sin phi. See, we have considered just this and this element, but we have numerous elements like this. All of their delta cos phi over here is getting added over here, and all of their delta B sin phi is getting added over this part. So what we have, B resultant will be equivalent to what? Delta B sin phi. So what we have delta B, it will we will utilize Biot's law, that is V naught upon 4 pi I dl sin theta upon r square. The distance over here is what? It is a square x square. So what we have, this is a square x square, then sin phi perpendicular by hypotenuse. It is a root over a square x square. This theta is basically tangent to the circle, so it becomes 1. What we have, this is mu naught upon 4 pi I, this is delta L. Suppose we integrate this out, it becomes what? It becomes 2 pi a. This is what? This and this get multiplied together. It becomes a square x square to the power 3 by 2 into a. And suppose it has n number of turns. So what we do is that we will utilize the formula of magnetic moment, that is n into I into a. See, over here we have n, this is I, a is what? Pi a square. Pi a square. So what it becomes? This is magnetic moment, and what we'll do is that we'll replace this mu naught upon 4 pi. This is 2. This is n into I into a. I will write as m. This is what? A square x square to the power 3 by 2. So what we will do is that we'll go for the special cases of it. What we have? V net. We have integrated out, becomes V magnetic field. Net magnetic field is how much? Is mu naught upon 4 pi 2m upon a square x square to the power 3 by 2. and we say that suppose x is 0, means point lies at the center of the circle. In that case, mu, it becomes what? Mu upon 4 pi 2m upon a cube. This is magnetic field at the center if x becomes 0. Now, another case is that when x square is very much greater than a square, in that case, what will have? V naught upon 4 pi, this is 2m. What do we have? This is, x is very large, then a get neglected, we get x cube. So basically what we have done is that what is the effect of current and what is the exact value of the magnetic field, which was set by Biot's law. It said that V naught upon 4 pi ideal sin theta upon r square, means magnetic field is directly proportional to the current, is directly proportional to the sin theta, directly proportional to the current carrying element, inversely proportional to the square of distance between them. And utilizing his formula, the Biot's law, what we did was we were able to calculate the magnetic field at the center of circular kinetic conductor. Then one of the most important, it comes everywhere in the magnetism, we see that magnetic field due to infinite conductor, that is mu naught upon 4 pi 2I upon a, and then finally we calculated that magnetic field of the axis of circular current carrying conductor. Over here we also utilize the magnetic moment part, that is basically N into I into A. A is basically area of the coil. That's all for today. We'll meet in the next class. Thank you.